everyone. So welcome. Appreciate it. My name is Mike Kochever. I lead the sales group here at OLI, and happy to have you joining us for this session. This is a new course for us. We haven't done this particular course before, and so we have Diana Miller, who's one of our corrosion experts and part of our application engineering team with us to give the training today. So we'll start with just a little bit of introduction. I think because of the size of the crowd, we're going to skip introduction of individual participants. Normally we try and do that if we have just a few folks on the training to get an idea of the types of applications you're working on, but I don't want to take up too much of our time and save that for application and investigation, looking at the software. So we'll do a bit of an introduction of OLI. I'll give you some background for those who may not know exactly what we do, how we approach simulation, and then we'll look at we'll get into the course. So let's go ahead and get started. We'll skip that one. So OLI has been in business now 49 years. We turned 49 on August 1st, and always with a focus on electrolyte thermodynamics and electrolyte modeling. So that's always been the mission of OLI, is to further the electrolyte science. By way of doing that, we've got a large properties database. So we have a team, the property materials group, that develops all of the components in our database. They regress all of the data that we find to make sure that we have the most accurate and the most robust modeling out there. We work typically in software, so hopefully everyone was able to get a copy installed so you can work along with Diana. That's how we like to approach the situation, is to get a copy of the software in your hands as the experts working with your processes, your systems. We want to make sure that you have the ability to work with those and make improvements as you can. We also do consulting, though, so if you have particular questions or small projects that you want to put up, we can work with that as well. So when we think of software in our offerings, we look at that generally in 4 quadrants, if you will. So we start with the chemistry. That will be one focus, especially of the first day today, is to look at electrolyte chemistry, and that happens in the OLI Studio. So Stream Analyzer you can think of as a virtual a virtual laboratory on your desktop. So if you want to study changes in pH or temperature and pressure and how that affects the system that you're analyzing, that's where we want to start. It's also the easiest way to kind of understand how we work with data input and then how that changes. ScaleChem is generally considered a specific tool for upstream oil and gas production. So this is a tool to help predict mineral scaling and the profiles along a production line. We won't focus on that particularly in this course, although we do have a ScaleChem course dedicated to just that tool that I think happens later this fall. So if you do have an interest in mineral scaling, especially in upstream, that may be one to check out. The other component of what we'll look at in this course is the corrosion analyzer, also a part of the studio. And what corrosion analyzer will do is to help compute corrosion rates, understand where you may or may not be at risk, what conditions you can work in, and then if you need to do some material selection, we can work around that also. Is carbon steel sufficient? Do we need to move to stainless or something even more corrosion resistant? We can talk through all of those types of calculations between today and Wednesday. The other types of tool that we have, so OLI Studio focuses on particular single point calculations. So if you have, think of it as a beaker of water or something like that, you can analyze that particular material or solution. In flowsheet modeling, what we're trying to do is model a full process. And we have 2 ways that we can do that. We have our own tool, OLI Flowsheet ESP, also another course that we're offering. So that will be next month. So this will kind of teach you the basics of OLI Flowsheet and how to develop models that look more at a process point of view rather than a single point. We also can connect OLI properties into our alliance engines. So this would be Aspen Plus or HYSYS, Pro 2 from Aviva, Unisim Design, Unisim Design from Honeywell. We have other partners as well. So if you already have models in those tools, the idea being you don't have to relearn a new tool. You can just create the models or work with the models that you have and bring in OLI to handle the thermodynamics for any electrolyte sections that you have there. We also can work finally in custom applications. I'm not going to go too much into detail there, but if there are ways to connect OLI into your own proprietary software tools and other third-party tools that aren't mentioned above in the Alliance engines. So we can always talk more with you in one-on-one if you have more interest in something like that. Inside of the software, then, we have what we call 3 frameworks, essentially 3 ways to solve electrolyte problems or situations. The first is the AQ or aqueous model. This is our long-time framework. It's based on strong electrolyte theory, and it's good for a wide variety of systems. This is something we studied well over our history. The problem with AQ can be that because it assumes that water is the dominant solvent, we can't go to very high ionic strength mixtures, and so the model starts to break down. So more recently, we've developed the MSE model, or mixed solvent electrolyte. This does not have that assumption of water, and so there's no concentration limit. We can go all the way up to 100% solute. Don't need water in the system at all to be accurate. You see still a very large pressure and temperature range that we can cover. I mention these two today because for the purposes of corrosion calculations, there are some tools in the corrosion analyzer that can work in all of the frameworks, but the corrosion rate calculations for right now are only in the AQ. We're working on developing the MSE model for corrosion right now, and hopefully that will be out soon. But Diana will get into an explanation more in detail of how to interact with these frameworks. They all come included with the software. You don't have to pick and choose, but you do have to make changes between the two of them sometimes to do the calculations that you want. So we'll get into all of that. The software uses the Helgeson equation of state for standard state properties. This has also been with us for a very long time. We settled on that as the most accurate basis for equation of state modeling. And then we have our own proprietary activity models. So this allows us to calculate the properties away from the reference state. And each of the frameworks above you can think of as a different way to handle that, a different activity model that it has. There are a number of papers that OLI has published that show all the equations and talk about how we've modeled these. We just don't release the parameters, obviously, as a part of our proprietary tools. In terms of the database, we've got about 6,000 species in the database and 80 plus elements of the periodic table. So you can see very broad coverage, very wide range of industries that we can cover. And you can define the software appropriately to assess the particular applications that you have. So we're going to look very quickly just at focusing on the chemistry aspect and the corrosion aspect of the software. So when we look at OLI Studio and all of OLI's tools, we do equilibrium-based solutions in 4 phases. So solid, liquid, vapor, inorganic. Usually, the second liquid phase we typically assume is an organic phase. And we're going to calculate speciation across the phases, and then physical and chemical properties of the system that you've defined. Again, for the studio, this is all point solutions. I don't know how much of the advanced mechanisms we'll get into, since this is not a stream analyzer course. We do that in the course there. But we do have ways to incorporate kinetic calculations, redox reactions, mass transfer, etc. So again, we can talk more in detail individually as you like. Just a reiteration here of the split between when modeling process design. We have our own tool flow sheet where electrolytes are primary. We do very rigorous chemistry here, so this is more of a tool for industrial water treatment where the process itself is very water chemistry centric. And then our alliance engines where you may be already working in other tools. So when we talk about corrosion then, which is the meat of the course for today, we look at thermodynamics of corrosion. So we'll talk about what we call stability diagrams, which are essentially a pore bay diagram in real conditions. This will allow you to understand, before you really get too far into it, where you might be operating in a place that where it's corrosive, where it's passivating, and then where the metal is inert. When we talk about corrosion inside the software, what we're really looking at is the corrosion of chemical attack. So this is the bulk solution in contact with the metal surface. We're looking at the behavior at that boundary, and we can predict then how that environment will or will not corrode. We can predict already general and localized corrosion. So we'll look at corrosion rates or pitting corrosion. And then we're looking at also in our development how to look at stress corrosion cracking as well, which is a difficult thing to model, but we are working on it. And then I don't know if the syllabus includes remaining asset life. So this is something we call extreme value statistics that allows you to compute based on information about a pit. It's a model that will tell you the time to failure of your asset, so we can look at some of that as well. That's part of the corrosion analyzer tool. Obviously, when studying corrosion, you want to understand what are the mechanisms, what's the chemistry that's causing that problem, and then we can start to look at predictions of either general corrosion or localized corrosion in those environments. And one of the big advantages that OLI has is to be able to do that in very complicated environments. So it's not just a couple of electrolytes in water. This can be many, many species all interacting with one another, and we can handle that. I mentioned allows you to do some material selection. So we have a pretty broad database of materials in the software that you can choose from. So you can set up a set of conditions, try that on, see how that behaves with carbon steel, and then change that to something more corrosion resistant to see if that changes the dynamics of your system. As always with modeling, we like to think of it as saving a lot of time, a lot of manpower, a lot of lab work, because you're working in the virtual world instead. You can focus those experiments, and then obviously reducing risk is huge. So if you can do a lot of these experiments virtually, you don't have to worry about working so much in the lab or having something happen on a live plant. So again, here's one of the stability diagrams. So we'll see the various regions and allow us to know where we're operating. Is there a risk of corrosion? And we look at how the ions partition. Again, that's kind of the studio's goal, is where does everyone split and how do they equilibrate? In calculations of general corrosion, we look then at the half reactions on the surface, and we do understand the diffusion layer. So we'll draw these polarization curves to understand where we have risk of general corrosion. This is where I should have mentioned, I'll go back one, and to say, so the stability diagrams exist in all three of the frameworks that we have, whereas as we get into the corrosion rate calculations, this is only in the AQ, so it's something to keep in mind as you're modeling. Likewise for localized or pitting corrosion, so we look at the relative potentials, so we look at the corrosion potential and the repassivation potential of the system, and where the corrosion potential exceeds, and that's where we now can get pitting corrosion on this curve. Diana will show you all of these as we go. And then I mentioned extreme value statistics. So this starts to look at time to failure of a particular asset. The thermodynamics of corrosion and cover our entire chemistry and all of the alloys and surfaces that we have in the database. And always we're developing new tools and new capabilities inside of the software. So as we have, when we start to add chemistry and alloys, it only gets better in terms of what we're able to model. I wanted to show one slide here just to kind of give you an idea of the types of alloys. I actually think these are not scheduled. That's an error on my part. These are now in the database. So these super chromes have been included as well. So this gives you some idea of what we're looking at. And I think with that, yeah, that's all I wanted to say by the way of introduction. I want to go ahead and turn it over to Diana and get everyone started. So thanks once more, everyone, for joining us. And I hope you enjoy the course.
Thank you, Mike. Okay, just give me one moment and I will start sharing my screen. And please let me know if you can see my screen and if my sound is okay.
The sound is good for me, Diana.
Okay, that's good, great. And can you see my screen?
I do not yet.
No? Okay, so something happened. Let's try again.
Now it's coming. There you go. Got it.
That is great. One last thing I want to do here is to show the chat so that I don't miss questions from our participants. Okay. Okay, I'm all set. Okay, good morning or good afternoon or good evening, depending upon your location. My name is Diana Miller, and today I will be your instructor. Today we will be learning how to do OLI corrosion modeling basics. We will be having a quick introduction to OLI Studio Stream Analyzer because when we learn how to set up our chemistry in Stream Analyzer, then we will bring this chemistry into our corrosion analyzer to perform our corrosion calculations. So after I finish that introduction to Studio, then we will focus only on the corrosion analyzer, okay? So that will be basically the structure of the course, a little bit of Studio, and then we will move heavily towards the corrosion analyzer. Today I will be using version 10 of the software. If you have a version that is a little older, let's say maybe a 9.6 or a 9.5 version, you may obtain slightly different results. But if you want to have the newest version, you are always entitled to just get your newest version for this course or for your applications from now on. And we will be also recording this course so that you have access to this content, maybe in the future if you want to remember how to do specific calculations, so you'll have the recording for you. Okay, so for the course objectives, we will be learning, as I said, Stream Analyzer and Corrosion Analyzer. Mostly the Corrosion Analyzer will be focusing on. And then we will learn how to choose our appropriate thermodynamic models for the chemistry we want to model. And we will be learning how to calculate different types of corrosion calculations. We will be learning how to do corrosion rates, how to identify or understand the propensity to localize corrosion, and understand Fourier diagrams. We will also learn how to enter water analysis so that you also can use those water analysis to perform corrosion calculations. And we will learn how to interpret all of our plots and results. Okay. So the class will be 3 hours. Each session. It's a total of 2 sessions, and we will be having a short break after every hour for each session. Just something I like to highlight here. If you happen to have only one monitor, it would be ideal if you could divide your screen. One would be the presentation that we are seeing today, and in the other half, you can put the software so you can follow the instructions and as you work, right? Like you can do it together at the same time. Let me know if you don't happen to have 2 screens so we can go through this exercise. You just use the Windows key, left or right key in the keyboard here, and then you can split your screen. You should also have access to both the corrosion analyzer and the stream analyzer manual, and we will be covering some of the examples for those manuals. And please let me know if you have the software installed. If not, then we can help you to finish the installation as soon as possible, and then you can just go through the course with no problem. So just let me know if you happen not to have the software installed in your machine. If you have any questions, just let me know. If you have technical issues, let me know. If you need to leave the course for a moment, or maybe you need to step out, let me know so that if I call your name, I know that you're not present. And if you have any mobile devices, it will be great if you could mute them so that it doesn't interfere with the recording. Please feel free to actively participate today. If this is an open forum, you can ask any questions. I will be happy to answer your questions or your needs. If you have any specific application that you have or you want to simulate, let me know so that at the end of the course or maybe in the second half of the course, we can go through those examples together. If you have questions, you can always raise your hand. I have the chat here next to me, so you can always write a question. I think I appear as OLI Systems, and you can just write privately, or you can just send a question to everybody in the chat, and I will be monitoring the chat if you have any questions. Or if you simply want to ask a question, please free and unmute yourself and go ahead and ask the question. At the end of this course, you will be receiving a certificate of completion, and you will also be receiving a course survey, which will help us always to improve this course. So that will be very nice if you could help us with that. And okay, let's start with OLI Studio. So as Mike was saying, OLI Studio contains these 3 different add-ons. We have the Stream Analyzer, the Scale Chem, and the Corrosion Analyzer. We will be focusing on Stream Analyzer and Corrosion Analyzer today. The Stream Analyzer will help us to calculate any electrolyte solution property, which is important because we want when we are working with corrosive environments, we need to understand or simulate in an accurate manner the corrosive properties or the aqueous properties of these electrolytes, right? We want to understand how do they speciate. We want to understand the density. We also want to understand the electrical conductivities, resistivities, and of course the pH. So all of this is very important. So we have 3 different thermodynamic frameworks to calculate these properties: the AQ framework, the mixed solvent electrolyte framework, and the mixed solvent electrolyte and Suavi-Redlich-Kwong equation of state. That basically is the MSc-SRK model. And we will probably go through all of this just to explain when to use which in our applications. We will also be learning how to enter molecular and ionic inflows to represent our corrosive environments. And that is all possible using the stream analyzer. Okay. Then we will learn how to calculate the general corrosion rates, the localized corrosion susceptibility. Then we will learn how to interpret these polarization curves and how to interpret these pore diagrams that the software calculates for us. Okay, so let me give you a brief introduction to the OLI corrosion model. So when we are studying corrosion in aqueous environments, the corrosion rates depend on multiple factors, such as the chemistry of the solution. Okay, so maybe we want to understand, we know that we have chloride species, for example. So we want to understand the concentration of those components. We know that the pressure also could play an important effect, temperature for sure, presence of known aqueous phases, such as acid gases, like CO2 or H2S. Then we know that the flow velocity also has an important effect on corrosion rates, and of course, the composition of the alloy under study. So here is where computational modeling becomes relevant because it allows us to get an understanding of each one of these factors, or any combination of these factors, right? You want to understand what's the effect of temperature and flow velocity, or just the effect of pressure, for example, okay? So the OLI corrosion model, the OLI corrosion analyzer has the ability to provide an accurate representation of both chemical equilibria and the thermophysical properties of the bulk solution. And at the same time, we can account for the phenomena at the metal solution interface, which is relevant to understand corrosion. So the OLI corrosion module uses two different, or the OLI corrosion model uses two different modules. The first module is the thermophysical module that will help us to calculate the speciation, concentration and activities, transport properties, okay? Because, for example, transport properties are important or necessary to predict mass transfer effects. And when we are working specifically in the OLI corrosion analyzer, we need to keep in mind that the only framework that we can use to calculate corrosion rates is the thermodynamic framework AQ, or the AQ model. We are working currently to also include the MSE corrosion, but that is under development. At the moment, anything that has water in water content can be modeled with the AQ model. So just is something that I wanted to highlight in here. Only the AQ model can be used for the OLI corrosion analyzer. For the second module, we have the electrochemical module, which for the second part that we use in the OLI corrosion model is the electrochemical module. Okay, and this is used to represent the partial cathodic and anodic reactions on the metal surface, and it is also used to reproduce the active to passive transition of ions on passivity for different alloys. For example, we will see what is the effect of chlorides and inhibitors on this active to passive transition of alloys. The electrochemical module is calibrated using experimental corrosion rates that are published in the literature. So if we have, let's say, stainless steel 304, what we have done is we have investigated different environments for 304 stainless steel, where let's say we find the corrosion rates in chloride environments, H2S environments, CO2 environments at different temperatures, different pH values, etc. And all of that experimental data then is used to calibrate our corrosion or this specific electrochemical module. Okay, so At a high level, the prediction of the corrosion rates starts by addressing three aspects of the corrosion kinetics. So the first one is the chemical kinetics, which is represented by the activation control model. Then we have the mass transfer, which is calculated using the diffusion control model. And passivity is calculated using the fraction surface coverage model. This fraction surface coverage model was developed internally at OLI Systems to understand the passivity of alloys in different corrosive environments. So this is basically what I just mentioned. The prediction of corrosion rates is done using the activation control. So in here, the Butler-Volmar equation is used for the activation control kinetics. The electrochemical transfer coefficient, this one, which is the alpha, and the exchange current density, they are both regressed from experimental data. Okay? Then we have the mass transfer or diffusion control, which is calculated also based on common empirical expressions that include diffusivity and viscosity, which are also calculated by the OLI transport property model, and is also based on regressed experimental data. And for predicting the passivity of a metal, we have the fraction surface coverage model, which was again developed for the prediction of the active to passive transition and the passive current density, specifically for these two parts, active to passive transition and the passive current density. The model parameters were also regressed from experimental data for specific chemical metal systems. So the combination of these three models is what allow us to compute the corrosion rates of alloys that are part of our database. Okay? And I promise this is the only theory that we are going to see, but I just wanted to show you how we internally, what we call the engine, in the background, how does it calculate the corrosion rates that we see in our simulations, okay? So this is how we do it. We have the combination of these three different models, and after we put them all together, then we calculate the corrosion rates. Again, validating it with experimental data. Okay, so now that I have covered that part, now we can just move to the software where we are going to study really quickly the user interface. It's important to understand which parts of the software does what, or where do you find information, or where do you change units, etc. So it's important to become familiar with the interface. So what we're going to do is we are going to open the software. This time, let me just minimize this. Oops, brought it back. Let's open the software. If you see your icon here, will be OLI Studio 10. Just double click on it. Okay. And you open it in a different place. So this is the software, and we will be studying the different windows or panels that you see in here, okay? So the first panel that I want to start with is the navigator panel. You see it here, okay? This navigator panel has different utilities or different ways that are very useful for us. We will be working a lot here in this navigator panel. The first function of this navigator panel is that you'll see here that there is a document 1. So in here you will open as many documents as you need or as you want. So let's say I add a new document. Here if I click on this icon, so you'll create a document 2 or a document 3, okay? So you start looking at or you have the ability to go back and forth from one document to another document. Okay, so that's the first thing that I want to talk about the navigator panel. The second thing that you can do in the navigator panel is to start creating your simulation. Okay, anything that is in here, anything that we start creating here in this navigator panel is any type of calculation or the definition of our chemistry. So you'll see down here there is this actions panel. Okay, and this actions panel has different icons. Actually, it has, in my case, it has even the icons for ScaleChem objects. So you'll see all of these objects, add oil analysis, all of this is ScaleChem. Probably you will not, if you only have the corrosion analyzer and the stream analyzer, probably you will not see these specific icons. You probably will see add stream, add mixer, water analysis, and the EVS calculation. Probably at these four. If you have them all, it's okay. It's probably because you have a trial, you will see all of these add-ons. Okay, so when you start creating a simulation here, you will start adding different actions. Okay, so let's say we are going to click on this add stream, and this is just for illustration purposes. So if you click on this add stream, you see that now the software adds in here a new stream. Okay, and there is now, you'll see that there is the global, and this is what we call the global stream. Okay, and down here is the stream level. This is what we call the stream level. So when you're at the stream level, you can always change units, you can always change the name of how you want to represent these components, you can always change the thermodynamic framework. A lot of options. You can always change anything at the stream level. If you want to perform a calculation to this stream, then we have different calculations. For example, we have the single point calculation. So you'll see now that we have the global stream, the stream level, and now we have a calculation level here. This will be the, let's say we want to calculate the pH in this specific calculation level. So I just want you to notice that in here you start seeing like a hierarchy. And the changes that you make at the global, changes that you make here at the global stream level, then will affect your stream level, and changes that you make at your stream level will affect the calculation level. So it always goes up, down. All changes will be affected from up, down. If you change units, let's say at the calculation level, then those changes won't affect anything at the stream level or at the global stream level. Okay? And we will, I am talking about this, but we will learn more about how to deal with changing units and all of that with our examples. Okay? So that is the navigator panel. I'm going to click here at the global stream level to bring all of my actions. Okay? And again, this is your actions pane where you select all the type of icons that you want to select, that you want to use for your simulations. Probably in your screen, the icons look like this. They are probably large icons. I personally don't prefer this presentation of the icons. So what I do is I simply right-click on this white area and select the option list. Okay? And that's why I see them this way. If you prefer to change it to this way, again, it's right-click and select the option list. Okay. Then we have some other parts of the software that we will be using a lot. The other part of the software that we will be using a lot is this tools bar here. This is the quick access toolbar. And in here, well, if you're familiar with this, the new, open, and save, cut, copy, and paste. These are probably, I don't use them as much, as the chemistry here, this chemistry that you see here. So you'll see that this chemistry it has different buttons. These buttons represent different options for our calculations or for our simulations. So let's say, what is this L1? This L1 is a button saying that the aqueous phase has been selected and is represented by this L1, liquid 1 or aqueous. VA is vapor, stands for vapor. SO stands for solid. And L2 stands for liquid 2 or organic phase. So whenever you have a hydrocarbon, the software will detect that you have a hydrocarbon. Let's say, for example, you have decane. So the software will turn on this by default. Okay? Because that is a second liquid phase or an organic phase. Then we will be playing with the next button. This RE button is the redox button. Okay? This redox button will allow us to turn on or turn off redox or reduction and oxidation states, or not states. It accounts for reduction and oxidation. Okay? So whenever you have different oxidation states in your elements, then you will come here to turn on or to turn off different oxidation states for that specific element. And again, we will do examples to understand how to use this RE button, the redox button. Redox stands for red, the RED, for reduction, and the OX for oxidation. Then we saw this, we have the MSC button, the MSC SRK, and we have the AQ framework. And we will be also using a lot this toolbar in here. This one is very useful. This one is for the first one, this one that looks like a binocular. There's a component search option. So whenever you have, it says if you click on it and you want to look for a specific component, let's say you want to look for benzene, you just type the component name here. The server will look for all the possible benzene components that it has in the database. And here will give you the structure of the benzene, all the phenolics here. Then you'll have the OLI tag, the molecular weight, Cas number, formula, etc. Okay. Now, something that I want to highlight in here. You'll see that the AQ framework here is highlighted in blue, meaning that it's selected. So we are looking, or the software, when you're using the component search, is looking only in this data bank, the AQ data bank. Components only in this AQ data bank. So if you want to search in the MSC, for example, you simply click on MSC and then go back to the component search and look for that specific benzene and see if we also have it in there. We do. Okay? So we have benzene, very similar information, etc. Then you'll have another option, which is the periodic table. Okay? In here, you can search components by the, let's say you know what elements it has in the molecular structure. Okay? So maybe it has carbon, hydrogen, oxygen, maybe some chlorides. Okay? So the software is selecting all of these elements and filtering by using all of these elements to find the component that you probably are looking for. And it will give you all of the options in here. Okay? So the search options is any of selected. So basically it's look for any of the selected elements here, or it has to be include only the selected. So it reduces your search even Even better here. Okay? So that is important. I think it's important to know that it is there, that option exists. Okay. And the last two icons that we will be looking at, let me close here, is this names manager, which is represented by this sodium chloride, NaCl, and salt. Okay. So basically, this names manager, what it does is to show, it basically will help you, or it will not help you, but it will match your preference. Do you prefer to see formula names on the software, or you prefer to display names in the software? So if you display the name, you'll see that immediately change it to water, okay? And if you display it to formula, then if you click apply, then you'll see that immediately it's in H2O. So it depends really on your preference, how you prefer to see the names for your simulations. Personally prefer formula. The OLI name is not very used. This is more like for internal use at OLI when we are doing some coding, entering new information, speciation. So we need to use the specific names of how we have them in our database, and that's the OLI name tag. So this one is really not that used unless you're I don't know, taking a regression class where you can enter your specific components in a private data bank. So then you will need to use the OLI name tags to do that. Okay, so I will leave formula. And finally, you have the units name, the units manager. And this units manager in here is basically we are going to learn how to change the units. If you click here in customize, you have the options to change units as you desire. You can always create a specific unit set. Let's say you'll see here there is units manager, you have metric, batch, mole. Let's say you can create your own units here because you always use a specific units, so you can create it here and add it to this list. Okay? But if you want to understand, for example, English flowing molar concentration, then you go to customize and see what those units are. You see that now volume is a beginning volume. This is square feet, then we have the pound small, etc. Okay, so you can always play with these units until you get the units that you like to use for your simulations. I will cancel this. I will cancel this. Okay, so that is the OLS desktop user interface. Maybe one last thing that I forgot to mention was this calculation output down here. In here, you will always see any calculation error. Let's say you have something in red down here, calculation output. This calculation failed. That means something went wrong with the calculation. And not usually, but sometimes the software will let you know what was wrong with the simulation. That will help you to troubleshoot the simulation. Okay. So this is what we already saw, and I will give you all of this for your information. So as I was saying, and Mike was saying, there are 3 thermodynamic frameworks. This is a slide that I have created just for reference when to use which thermodynamic framework in your simulations. As a general rule, I have found that if you have more than 70% of the stream is aqueous, or basically you have a diluted solution, then you can use the AQ framework to calculate your electrolyte properties. Okay. Then if you have the mixed solvent electrolyte, let's say this one is very useful when you have a solvent that is different than water. Okay. So you have your solvent is sulfuric acid or methanol or ethanol, any other solvent that is not water. This mixed solvent electrolyte works beautifully for those systems. Or when water is present, but water is not the dominant component. So that one can be also can be used for that, for those specific scenarios. And the MSCSR case was developed for oil and gas applications. And any chemistry that contains CO2, H2S, and requires high temperatures and high pressures above 80 atmospheres, then is when we use the MSCSRK. And again, we'll do examples to understand this and reinforce these concepts. Okay. So when we go to the software, we will see different calculation types. And these calculation types, and here I have divided them into the stream analyzer and the corrosion analyzer. When we need to define our chemistry, there are two options. We add a stream, we enter a flow in a molecular way, and then we have the other option, which is the water analysis. And here we enter a chemistry using the ionic composition. You have the composition, a water analysis that has cations and anions, and then we use it to recreate a corrosive or a stream environment. For the different types of calculation, we have in stream analyzer, we have the single point, survey, mixer, and chemical diagram. And for the studio, we have the purvey and the corrosion rates. We will touch on the single point and add survey options, and then we will go to the stability diagram and corrosion rate. Okay, so let me just bring the software one more time. I want to talk about these different single points that we have. I'm going to close these documents here. So right click on document 3 and say save changes. No, I don't want to save changes. Right click and say close. And we're going to stay in this document here, okay? So what we're going to do is first go to File and let's save this document. Save as. We're going to start saving our simulations. Create a file and saving our simulations. I'm going to find my specific folder and let's name this. What would be training? CMB A1. Okay, just click save. You see that now it no longer says document 1, it says training CMB day 1. Okay, so the first thing we're going to do is we're going to add a stream. So there are two options to do that. The first option, just give me 1 second, there is a comment here. Thanks. Oh, okay, there was an error for a specific login error. Okay. Yes, it's taken care of. Yeah, there was a question in the chat. I'm just checking what was the problem or the question. Yeah, so I will take probably 2 minutes about to explain this, and then we can go for a break. So the first thing we are going to do here is we're going to add a stream, okay? And there are two options to do that. You can go here to the Actions pane and double-click on it, or you can go to the menu bar and click Streams, Add Stream. Okay. So now you'll see that you have a workspace where you can start entering your data. And to the right, you see a button that says Add Calculation. So if you click on Add Calculation, there is a single point option. So just click on that single point, okay? And you'll see, again, you have a single point form here in the left. And to the right, it says type of calculation. It says isothermal. So you'll see, if you click on isothermal, you'll see a list of different calculations here. 13 different calculations. You have the isothermal, bubble point, dew point, vapor fraction, set pH. Okay? Isothermal is basically a calculation that happens at one temperature and one pressure. Okay? Isenthalpic, I forgot the definition of isenthalpic. I think I have it here. I have created this slide here. It's a constant heat loss gain is applied to the calculation, and temperature or pressure is adjusted to meet the heat content. That will be an isenthalpic calculation. Okay. Then we have bubble point. This is for to calculate the boiling point. Dew point to calculate the condensation point. Vapor amount and vapor fraction. This is, for example, when you have evaporations and you want to simulate the amount of vapor that you have in the vapor phase. You have isochoric, that is basically constant volume. Set pH, which is to basically calculate or set the amount, the pH, the targeted pH that you want for a specific stream. Precipitation point, this one is to calculate the solubility point, the solubility of a salt in water. Composition point, let's say you want to meet a specific, you want to meet a regulation where it says H2S cannot exceed 0.02 ppm in the vapor phase. So you will use this composition point to do that. Reconcile alkalinity to calculate your alkalinity, and we have autoclave calculation. This one is specifically designed for corrosion rates. And then we have the custom, not corrosion rate, this is for corrosion experimentation. When you are doing high temperature, high pressure experiments. So you have your autoclave. And the custom is anything that you don't see here can be calculated. Maybe we just haven't put it in the list, but you can create your own type of calculation. So, for example, I use this custom calculation to calculate the solubility of a gas in water, for example. So I use it there a lot. Okay, so those are the calculation types I wanted to talk about. And let's take a break of 5 minutes. So we will meet the 5 minutes after the hour, and then we can start actually playing with the software. From now on, everything will be just hands-on, okay? And the theory part is done. Now we are going to start actually doing examples in this second hour, okay? So I'll meet you at, here is my 10:01, so I'll meet you at 10:06 or 6 minutes after your hour, wherever you are located. So I'll see you in a moment. I'll mute myself. I'll be here if you have any questions in the chat, but I will mute myself now. Going for some coffee too. Okay, I'm back. Is everyone back? Let's see. You can always raise your hand or just unmute yourself and say here. So I know that I have the majority of people before I start. Okay, so I don't have anybody back yet.
Yeah, there are a few coming in the chat, Diana.
Oh, okay, yes. I have the chat and the participants in a different window.
Yeah, I see quite a few.
Great. Good. Thank you, Mike.
Of course.
Okay. So I'll wait maybe 10 more seconds and then I will get started. Okay. So we were talking about, before the break, we were talking about the types of calculations. But I am going to start a new example, the first example for today, and that will be an isothermal calculation. So what we're going to do is let's right click on this string, let's delete it so that we can start from scratch, so that we all have start at the same time. Are you sure you want to delete string? Yes. So we should start with a blank navigator panel here to the left. Okay. So the first step, or the first calculation that we are going to do today, is to calculate the properties of 1 mole of iron, elemental iron in water. Okay. We are going to learn how to set up an isothermal calculation, and then we will explore where to find the results for this specific simulation. Okay, so the first step is, as I mentioned before, you just double click here, add a stream, or the other option would have been streams, add a stream. Would have done the same trick. Okay. And the next step is to change its name, okay? Because it's important, I guess it's important that we make sure that we understand what calculations we are doing. So if we change the name, that will give us an idea of what chemistry we have or calculation we are doing, etc. So if you have different options to change the name. You can double click on it, you can right click and select rename. You can hit the F2 key in your keyboard, or simply go here to the first tab that says description, and there is a name section where you can name it. You can name the stream. So you can put, for this specific example, we are going to rename it isothermal. Okay. And down here in the description, we can always add more details. Sometimes it is, from a simulation point of view, it's important to always give a little bit of a description of what you're trying to do for your simulation. So for here, let's say isothermal calculation of 1 mole live Fe solution. Okay. So once we do that, then we go to the definition tab, which is the next one next to description. Okay. You click on it, and the next step is to start adding your chemistry. You'll see that there are 2 sections here. The first section is the string parameters. This string parameters has 3 different types of information. It has the stream amount. I'll explain this a little bit. It has the stream amount. Basically, it's saying what is the size of the stream. Then you have the temperature and the pressure. These two values are always there by default. 25 degrees C and 1 atmosphere, room temperature, okay? And atmospheric pressure. Just 25 degrees, 1 atmosphere. Down here on the inflows is where you define your chemistry, okay? Notice that by default, the units are moles, degrees C, atmosphere. If you want to change these inflows, for example, directly, you just click on the hyperlink. You see there is a hyperlink here in mole. It opens the units manager, and you'll see, you look for inflows, and you'll see inflows here, and sure enough, it's defined as moles. You can always change it to whatever you prefer, mass, concentration, etc. But for this example, we're going to leave it in moles. So let's cancel that. Just want to show you the ability to change the units here with the hyperlink. We're going to add iron in our system. So this is elemental iron, right? So we put Fe. We're going to add, for the value, we're going to add 1 mole. So now you have 1 mole in 55.5082 moles of water. This 55.5082 moles of water really is the same as 1 kilogram of water, okay? So as you know, the unit 1 mole over 1 kilogram of water is molal. So we have here 1 molal solution of iron in water. Notice that the stream amount now, this one, is the green cell that you see here now says 56.5082 moles. So what this is doing, whatever cell that you see in the software that is green means that it's being calculated by default. So this green cell is adding these two amounts that you see here in the inflows, okay? Additionally, anything that is yellow cannot be edited. So if you click on these yellow cells, the software will not allow you to delete, to override, nothing. It just is constant. And anything that is white is anything that you can modify or anything that you can delete or overwrite, okay? So once we have created this string here, the next step is to add a calculation type, okay? So we are going to add, to go to the right here where it says add calculation. We're going to click on it and we are going to select single point, okay? So again, you'll have the single point here. It's a hierarchy. It's under the isothermal calculation. And we are going to rename this as 1 mole of elemental iron, 1mFe, okay? So once we have done all of this, then we go, and you'll notice that you have a calculate button now, and then you have, it's green, indicating that you can go ahead and calculate. Okay. So the calculation is complete. It took less than a second. And you have different ways to analyze your results. Okay. You can analyze the results here in the summary tab. Again, this is just a summary information, nothing detailed. It will tell you the type of calculation, at what conditions. It will tell you how much you have in your aqueous phase, your vapor phase, and your solid phase. It will tell you the properties of your electrolyte or your solution. So you have pH, ionic strength, density. But again, this is way too like a summary. This is it's a big overview. So there are two ways to see more detailed information. The first way is to go to the output tab. So you see down here where it says input and output. If you click on the output tab, so it will take you to something that looks very similar to your input, but now in here in this gray area, you can start adding information, okay? So if you right click on any of these gray areas, you go to sections, So again, right-click, sections, and then you have all of this information you can add. You have additional stream parameters, phase flows, thermodynamic properties, pre-scaling tendencies, what is in the aqueous phase, vapor phase, solid phase, molecular totals, and MVGs that stands for material balance groups, activity coefficients, K values, Gibbs free energy, partial pressures, etc. For this calculation, I'm going to click on additional stream parameters, and you'll see more detailed information about every single phase, about density, ionic strength, pH, liquid volume, etc. Okay, so your pH here is, it's basically 6.99. The second way of analyzing the results is to go to the report tab. You'll see you have your description tab in the top, definition, and then you have the report tab. You also are seeing probably this file viewer I have here. This is something that I turn on. It's usually turned off by default, so maybe you don't see it there. And don't worry about that. We don't need it for this training, or for any type of calculation. We don't need it there. I sometimes use it, but please forget about this. We don't need it for this training. So let's click on the report, the second way of analyzing data. And the report will give you a lot of different tables, okay? If you scroll down, you'll see several tables. You have stream parameter, total and phase flows, scaling tendencies, species output, element balance, element distribution, okay? So this stream parameters is basically what I just showed you in the output table, all the ionic strength, densities, etc. Then you have the total and phase flows amounts. I really like this table because it allows me to see everything, all the information that I enter in moles or in mass. It converts everything for you in mass or in liters, depending upon what you prefer. If you are a mass person, a moles person, or a volume person, this table always do the calculations for you. Okay, so you'll have any of the information you want in either moles, mass, or volume. Then you have the scaling tendencies. We don't have, apparently, no scaling tendencies here, so nothing is reported. We have the species output table. And this is important. This species output table is basically the speciation of your components in water. In this case, we are not having really a speciation because we added elemental iron. And you'll see that elemental iron, in this case, it just didn't dissociate, it didn't create any cations. Like if you would expect that it will be oxidized, right? But it just stayed as elemental iron. And then you have the dissociation of water, so you know that it is 1 times 10 to the minus 7, and that's what you expect. You have for both H plus and OH minus, okay? And you total amount of water, okay? Then you have the element balance. Element balance, I like this table because sometimes maybe you're tracking a specific oxidation state, and this table is giving you, or is adding, or yeah, it's basically adding all the species that have this oxidation state of H plus 1, right? All the species that have OH minus, oxygen minus 2, and all the species that have elemental iron. So in here you can follow one specific oxidation state, okay? So this hydrogen plus 1 is combining the amounts of hydrogen plus that you see here, plus the 2 molecules of hydrogen that you see here. So that is what it's doing. And the element distribution, which is basically the same information, but now it's giving it just in a mole percent or in a percentage way. Okay, so that is, if we go back to the definition, and we click on input, we go back to our original calculation. So that is an isothermal calculation. Everything was calculated at 25 degrees, 1 atmosphere. But now the question is, why the iron didn't form any, basically it didn't oxidize. You would expect that it will oxidize, right? In these conditions, in water at 25 degrees C and 1 atmosphere. So what happens is that in the software, we need to account for the redox reactions. So in our calculation that we just saw, we did not turn on redox reactions. Okay, so for the iron to go to a specific oxidation state, we needed to tell the software, okay, iron is going to be is going to oxidize into iron plus 2. Okay, so what we need to do is to account for that, for those redox reactions, for that oxidation reaction, and to do that is just simply turning on the redox button. Okay, so that's what we are going to do. We're going to turn on the redox button. So we go back to the software. And what I am going to do is go back to this isothermal calculation, okay, and add a single point, okay. That single point is going to be isothermal, okay, and we are going to rename it FE oxidation. Okay, so you'll see that everything stay the same as we defined. Iron 1 mole, 55.5082 moles of water. The only difference is that the redox reaction button is not turned on. So we need to turn on the redox. Just click on it. And you'll see that now it turned blue. Okay? When it turns blue, you'll see in the summary section that it says redox has been selected. Okay? So what this means now is that now we are going to account for this oxidation reaction here. Okay? We're going to say that iron is going to oxidize into iron plus 2. It's going to release 2 electrons, okay? And this second reaction, now, we usually, once we have an oxidation state, an oxidation reaction, we need to have a reduction reaction. So this hydrogen will be the one that is going to be reduced. So the charge goes from +1 to 0 to produce this molecular hydrogen. So down here you'll see the balance equation showing the element that has been oxidized and the element that has been reduced. Okay? And all of that is going to now occur because we turn this redox reaction button on. Okay, so now that we turn it on, then go ahead and calculate. Okay? And to analyze the results, again, you can always check the summary section. Notice that the pH increased. Now we have a pH of 9.3. And the oxidation reduction potential of this solution was also calculated, okay, because we turned that redox button on. Then we go to the report. I want to analyze a specific table to see what happened now with this calculation. So again, you have stream parameters, etc. So maybe if you don't want to every time scroll down, you want to go specifically to your preferred table. So you will go to just go here to this option that says jump to, and just click on that and just select the table you prefer. So in this case, we're going to analyze the element balance table, okay, which is usually at the bottom of the report. So this element balance table is very useful because now because you know, like it will give us the elements with the respective oxidation numbers. Now notice that iron is here. Iron class 2 has been formed. You have 1 mole of iron class 2 total. And if you continue looking at the table, some of it is in the aqueous phase and some of it is in the solid phase. Actually, most of it is in the solid phase. Then you also see that some of the elemental iron was also oxidized to iron class 3, but really it's very small amounts, very small amounts. And it's mostly in the aqueous phase, okay? And notice that now you don't have any elemental iron, okay? You don't see any elemental iron here. All of it has been oxidized, okay? So this means that, that the elemental iron was completely oxidized and gave up 2 electrons to become this iron class 2. And most of it now is in the solid phase. And I will explain which solid phase was formed in a minute, okay? Now, those 2 electrons that were freed will be picked up by the hydrogen class that is in water, okay? And those hydrogens then will be converted into molecular gas or hydrogen molecular hydrogen. So you'll have here, you see H0 that represents your reduced hydrogen, and you see that 2 moles have been formed. Okay, so some of it stays in the aqueous phase, but most of it really is in the vapor phase. So we are producing molecular hydrogen. Okay, we are basically, as the reaction occurs, we see some bubbling going up because we are forming this molecular hydrogen. Okay, so that's what happened here. We had an oxidation and a reduction, but we also saw that we are forming a specific solid. Okay, so what we are going to do is going to scroll up and go to the species output table. And in here, you'll see all of the species that have been formed in this system and the dissociation and how much of each one you have in the system. Okay, so in this case, it's saying that iron hydroxide has been formed, total amount of 0.999, almost 1, 0.1. Sorry, almost 1, and all of it is in the solid phase, okay? So why are we seeing the iron class 2 as an iron hydroxide? The reason why is because when the electrochemical reaction happens, we have this iron class 2, okay? Then we'll have some hydrolysis reaction that occurs. The iron class 2 reacts with water and then will precipitate out this hydroxide, iron hydroxide. This is iron 2 hydroxide. And then this is what will end up forming at the conditions that we have. And that's why we are seeing this iron class 2, or this iron 2 hydroxide here. Okay, any questions? Maybe I'm just going too fast. Do we understand why we have to turn on the redox in order to account for the oxidation state of iron, etc.? Just let me know. You can always write a chat. Remember that you are all muted. So if you want to talk, simply just go ahead and unmute yourself so that you can ask questions. Okay? And all of these that I am going through, I'm going through because we will be needing all of these redox to do corrosion rate calculations, and it's most useful when we are doing 4-by diagrams. Okay? So that's why we are spending a little bit of time on this basic calculation. And because we are getting familiar with the software as well. Okay, so there is a third example I want to talk about, and now is yeah, we had a very easy chemistry so far. And we know that iron belongs to these transition metals in the periodic table, okay? Now, the software, when we have a transition metal, when we have defined a transition metal in the inflows, the software easily recognizes that. There is a question here. Question, is there a way to have the redox setting active by default? Yes, there is a way, but I wouldn't recommend it, because when you turn it on by default, and we'll see in the next example, sometimes you don't want to include all of the oxidation states for your calculations, because it creates more components, or probably is not relevant for your temperature, pressure, or your conditions. So it's always good to turn it on when you are certain that you are going to have redox reactions, okay? When we are doing corrosion rate calculations and when we are doing pore diagrams, the redox reaction will be always turned on by default in those specific calculations. So when we are doing calculations like this, isothermal, it's not recommended, because maybe you will see in the next example that we will be adding a lot of information, and that maybe it's not even necessary for your simulation. And even in the pore diagrams, in some cases, we need to be preferential on the types of elements that you want to turn on and turn off the oxidation state. Okay, so we will cover that in more detail. Okay, so we're going to have a third example, and here, let's say, I was saying that the redox reaction will always identify the transition metals from the periodic table. If you don't have a transition metal, something like sodium, something like in the first group of the periodic table, it's not a transition metal, so the software will not turn on the redox on by default. So let's do an example. We go to the isothermal calculation, and we are going to add a single point. And we are going to rename this iron in sodium sulfide. So what we're going to do is, in the inflows, we're going to add sodium Na2S sulfide. So you just make sure sodium sulfide, and we are going to add a tiny amount, 0.1 moles. Okay. And then we make sure we turn on the redox. Check that we have the redox selected here. And I want you to notice something. There is a drop-down arrow next to the redox. And if you click on it, you'll see that only the transition metal was selected. That is iron. So we added to the system sodium, and we added to the system sulfur. Okay? And the software did not turn them on by default. So it's going to take into account only the iron. And for sodium and sulfur, the software will assume that the oxidation state of sulfur is -2, and that the oxidation state of sodium is +1. Okay? So we are going to live with that. We go ahead and calculate. Okay? And then we go to the report. And again, I will use the jump to element balance. And in here we'll see what's going on. We'll see what happens here. So we'll see that still, okay, we already know this. We form 1 mole of iron +2. And now you'll see the sodium oxidation state here. And then you'll see sulfur -2. Okay? The sulfur -2 is most, a little bit of it is in the aqueous phase, okay? But most of it is in the solid phase. So now we are forming a solid that contains sulfur -2 and a solid that contains iron +2. So we scroll up to this species output, we'll notice that the software, sure enough, is predicting what we already knew, 0.9 moles of iron hydroxide and a little bit of this iron sulfide or pyrrhotite. This is 0.1, okay? So to form this pyrrhotite, the sulfur is stealing 0.1 moles from the iron +2. So that's why you don't see here a mole of iron hydroxide. We are forming these two solids. And again, the sulfur just assumes that the sulfur is only in the oxidation state of -2. Okay? So pyrrhotite has oxidation -2, S is -2, and the bisulfide ion has oxidation of -2. So all of these components will have only oxidation state of -2 for sulfur. So what about if we turn on the oxidation state for sulfur, all of them? What happens? What can happen? So we go to the redox, and then we click on this drop-down arrow, and we click on sulfur. Just enable it. So now we have both iron and sulfur, okay? And then we recalculate. So again, I just use the drop-down arrow and simply click on the sulfur to make sure that it's selected, and then click calculate. And then we go to the report. In the report, we see the pH, which is also very high. But we want to go to the element balance, so jump to element balance. So now I want you to notice something here. Oh, there is a question here. For Ari, did you select sulfur? Did you select sulfur? So I'm going back to the definition. And the previous calculation, I only selected iron, okay? And it's going to assume the oxidation state of -2. For this new calculation, I go to the drop-down arrow next to the RE button, and then I select sulfur. So just click on it. And just make sure that we selected it, just click on the drop-down arrow again. And you'll see that they both are selected now. And we recalculate, okay? So with this, once we go to the report and then we go to the jump to element balance, I want you to notice something here. I have selected the sulfur redox, and all of the oxidation states of sulfur have been included in this calculation. So notice you have sulfur +4, sulfur +6, sulfur -2, sulfur +2, sulfur +8, sulfur +3, sulfur +5, and elemental sulfur. 8 different oxidation states that sulfur has, and we have included them all in the calculation, okay? Now, notice that really it's a very small amount. Really, like in here, it's for sulfur +8 is to the -100. That is virtually 0. But because we are instructing the software to include them, the software is doing that, okay? But really, the only oxidation state that matters, according to this calculation, at 25 degrees C and 1 atmosphere, is that the -2 is the most stable species, and is the only one that is really forming from that 0.1 mole that we enter as sodium sulfide. Everything else is virtually 0, right? But you have included the oxidation state of sulfur. Now, if we go back to definition, let's say, okay, I don't need to enter all of those oxidation states. probably I need to enter the elemental sulfur and the -2 oxidation state. I know those are the ones that have been measured, or that I am certain that I am having only those. So when you don't want to enter all of those sulfur oxidation states, you have an option to turn off the other ones manually. So how do you do that? You go to the chemistry tab, so go to the menu. There is the chemistry tab, and you click on it. We are going to go to the option that says model options. We go to model options, click on it, and that will open a new window. In this new window, you'll see that there are 4 tabs, and we are going to go to the second tab that says redox. Okay. And of course, we have turned on the redox on, so this is checked, saying that we are including redox reactions. And for sulfur, we are including them all, but we are going to expand it. All of them have been selected. We don't need them all. For this calculation, it's not necessary. So I'm going to unselect here the sulfur, and I'm going to select only -2 and 0. That's it. I don't want any other component. I don't want any other oxidation state. Just those 2. So I make sure I check on this this sulfur -2 and this elemental sulfur, and then I click OK. Once I do that, then you can go again to this redox. Next to it, there is this drop-down arrow, and you'll see that now only those 2 oxidation states are being taken into account. Okay? So I leave it like that, and then for the one more time, we will calculate this. And we'll see pH, ORP. I didn't track the ORP, but the ORP changes when we also have or take into account different oxidation states. We should have been able to, we should have tracked this number, but I just forgot. But it's important to know to state that when you select or you don't have a specific oxidation state selected in the system, then the ORP value is going to change. Oxidation reduction potential of the bulk solution is going to change. Okay, so let's go to the report. And in this report, we go again to element balance. And in here you see the table is much shorter. We're not including as many oxidation states for sulfur. And you'll see that, yes, we have sulfur -2, but the sulfur 0 is also here, elemental sulfur. And it's really probably virtually 0 as well, a very small amount. And that will be in the aqueous phase. And nothing else has changed. We have still the formation of iron sulfide and iron hydroxide. Iron sulfide and iron hydroxide. We want to double check. We come up here. This is output where we will see the iron hydroxide and the iron sulfide. And maybe you start seeing elemental sulfurs. I don't see the elemental sulfur here. Oxidation state, but you will see the for example, the -2, again, the H2S, that is all the ones that we are including for minus the oxidation state of -2. Okay, so I know this was a lot of details, but it's important to understand these details, especially when we are working, let's say, in 4-way diagrams. Do we include sulfur? Do we include carbonates? What do we include, and which oxidation states are the most relevant ones? So it is important to take all of this into account. And also, if, like I just showed, if you turn on all of the oxidation states, probably you will be generating a very long report with data that probably is not relevant or meaningful. So it is always important to know I don't know, like if in your experiment you're certain that you are having some oxidation and some specific reduction reactions, and that oxidation reaction is creating some specific oxidation states, those are the ones that probably we should take into account for our simulations. Okay. I have a question here in the chat. Somebody is asking, is the oxidation reduction potential and the OCP are the same? Are those the same? The answer is no. This oxidation reduction potential is specifically for the bulk solution. It's the potential that you measured. Let's say you have a platinum sample, a platinum electrode, and that is what you are measuring in that, the oxidation reduction potential of that specific bulk solution. The OCP that we will cover in our polarization curves is the open circuit potential. So that is the potential that the metal that you are studying, let's say an alloy, let's say it's 316 stainless steel, when you add a metal into your solution, into your bulk solution, that metal is going to reach an open circuit potential or a rest potential, okay? And that is the potential that is measured for that metallic sample or for that electrode under study. The ORP is simply measured for the bulk solution, okay? So that's the difference. One is for the bulk solution and the other one is for your specific electrode under study, which is generally an alloy, right? So that's the difference there. Okay, so that is regarding the redox reactions. Now, when we are working in corrosion rates, or when we are calculating corrosion rates, we need, sometimes in some examples, we will have a gas that has a condensable component in the chemistry, and we know that there will be some condensation, and that condensation will cause corrosion damage, okay? We also know that the pH is also an important parameter when we are calculating corrosion rates, okay? So what I am going to do here is I'm going to go through two basic calculations, maybe the autoclave. If somebody is interested to know or to set up, to learn how to set up an autoclave, we can do it maybe in the next class. But today I'm going to focus on these two because I find them very important when we are working on corrosive systems. So I will focus on these first two, and then we can, if there is interest on the autoclave, then we can talk about this one next class. Okay, but these two are very important to learn how to understand them and set them up so that we can be successful calculating corrosion rates later on. Okay, so these two examples I promise will be short and they will be simple. So the first example that I am going to talk about today is the dew point. The dew point is defined as the temperature or pressure at which a condensable component of gas, a condensable component that is present in a gas, starts to condensate into a liquid, okay? Again, so let's say in this case we have that our chemistry is methane, CO2, and H2S, okay? And we have a very small amount of water. But when this gas condensates, it's going to bring, when this water condensates, it's going to bring some of these gases. They are going to dissolve into the water, and that's going to reduce the pH. And that is something that can be detrimental for metallic materials, okay? So we want to evaluate what is the pH of that condensed phase, and that will help us to determine how aggressive it will be for our materials. Okay, so let's go back to software, and we are going to set up our next calculation. So we are going to add a new stream, okay? Just click or double click on this add stream, and let's rename it, double click on it and rename it dew point. Oops. Okay, so this dew point, I want to use the MSC framework for this calculation. So just use, select the MSC framework. So you'll see to the right, the chemistry model is now MSC. And I also want to change the units. To do that, so I make sure that I'm selecting the dew point. And I go to my units manager, okay, the CF icon here, to change the units that I want to use for this example, okay. So I am going to click on this units manager, and I am going to change this metric batch moles to metric batch mole fraction, okay. This metric batch mole fraction, then you can see, click on this customize to see what were the changes that happened here. So mole fraction was defined for inflows and for the output variables in our report. Everything is going to be in mole percent, okay? And our stream amount still remains in moles, okay? So we're happy with this, so then click OK and click OK. So notice that now my inflows here have changed to mole percent. And what we are going to do next is to define the stream parameters, okay? So let's say that you have 100 moles of the gas, so you overwrite that 55.5082. And then we have 120 degrees C. And we have 1 atmosphere of pressure, okay? The next step is to add your chemistry, okay? So your chemistry contains water, which is already added by default. This is an electrolyte software, so it requires water in the system. Then we have methane. This is 94% mole, and this is CO2, 3% more. And H2S, that is only 1%. So we have methane, CO2, H2S, and a small amount of water, 2%. Okay? So let's add a calculation to the right, a single point. Okay? And we are going to, instead of using this isothermal option, what we're going to do is click on it, and we are going to select the option dew point. Okay, you click on dew point. There will be only one change in the workspace here. Now you have a new section that says calculation parameters. And what this means is the software will calculate the temperature at which the first drop of water will condensate or will form, okay? The software also calculates the pressure. Let's say if you click on temperature, you'll see that there is a drop-down arrow, and then you can select pressure. So in this case, now it would be the software will calculate the pressure at which the first condensate or drop of liquid will form, okay? Obviously at a constant temperature. For this example, we are going to select the temperature option. So the temperature option means that we are going to keep the pressure constant. So you'll see there is a brown dot here that says the calculation specification is fixed. So we are going to keep the pressure constant. But the temperature now is in green, indicating that it's going to be changed. This is the initial value. Really, we are going to calculate the temperature at which the first drop of water forms. Then we go ahead and, before we calculate, let's change this single point name to dew point temperature. That will be DPT, dew point temperature. And then we go ahead and calculate. So in the summary, we'll see that we have a pH of 4. Okay, so this is a very acidic pH, especially if we are working with, I don't know, a carbon steel. Maybe this is very aggressive, right? So this water is acidic. Now we need to understand why it's acidic. What is happening? So what we are going to do is we go to the report, okay? And we are going to scroll down until we find the species output table, okay? And in this table, you'll see all the species, okay, that are being formed in this system. This system it has two phases. It has the liquid phase and it has the vapor phase. The liquid phase is the first drop that was formed, okay? Maybe I should have talked about that. Just let's go back for a moment to this total and phase flows table. So notice here that from the 100 moles that we added in the system, 99.99% of it, or 99.999 moles of it, is in the vapor phase. And only a tiny fraction is in the liquid phase. So it's a very small drop. That is 1 times 10 to the minus 4 moles. So this amount is a very small amount. It's the first condensate that was formed. Okay? And the temperature at which that first drop of water was formed was at 70 degrees C. So you had to really decrease the pressure, the temperature of the system in order to have the first condensation happening, okay? So if we go back to the species output table, now we'll see that after that condensation happens, so you'll have a liquid phase and a vapor phase, a very small amount of liquid, and this is the composition of that liquid, okay? This is the composition that we are interested in, especially if we are talking about corrosion. So, what do we get from this? So remember, we entered 3 mole percent of CO2 and 1 mole percent of H2S. But notice the distribution of these species in the aqueous phase. You'll see here that they are virtually the same. This is 2.3 and this is 2.04 10 to the minus 3, but they are the same order of magnitude. This is interesting for me to highlight here because notice that in the solubility of H2S is the same to that of the CO2, but really you needed 3 times of CO2 in the chemistry to reach the same amount of material in the liquid phase. Okay, so that means that H2S, this indicates that H2S is more soluble than CO2. Okay, you need 3 times more CO2 to get the same amount of CO2 in the system. So this is important. So now, when you dissolve CO2 and H2S, that is going to create more acidity in the solution. They are going to dissociate. They are going to create more H plus dishydronium ions, which is the same as H plus. And you're going to increase the amount of hydrogen plus in solution, and that will decrease your pH. Okay, so that is the dew point. Then we will learn, this is how to set up this calculation. Later today, we will learn how to use this information and then perform corrosion rates on that specific liquid 1 stream or liquid 1 composition. Okay, so it's the top of the hour, so we're going to take around 5 to 6 minutes of a break, and then we'll move on to a second type of calculation, which is the set pH, and after that, then we start creating corrosion rate or going through corrosion rate calculations. Okay, so I'll see you at 11:06 or 6 minutes from now. Okay, I am back. So, please let me know who is here on the chat, or you can just simply unmute yourself and say, I'm here. Oh, cool. I feel like these breaks are so short. They happen so quickly. Oh, God. That's good. Thank you so much. I see a lot of people are back. I also had a question before I left to the break. The question was, so the pH is calculated at the dew point temperature. So to answer that question, yes, the answer is yes. If we go back to the calculation for the dew point, you'll see that the first drop of water forms at 17.6 degrees C, okay? And the pH will be reported only for the aqueous phase. So that is the pH that at this temperature, the pH is 4.6. Okay, so yes, the answer to your question is at the dew point temperature, this is the pH. That's correct. Because we needed a liquid phase to calculate that pH. I hope that answers your question. And then we are going to move to another simple calculation, which is important to also know how to set up, especially when we're dealing with, let's say, you know that you are having corrosion at a specific pH and you want to neutralize a sample. So it is important to learn how to do this calculation to avoid corrosion damage. So this set pH usually I have seen it being used for analyzing or designing a process, but it could be also used to meet operational pH to reduce corrosion rates. I don't know, maybe in pipelines. Okay. Another example could be maybe neutralizing a waste stream for its subsequent disposal. Okay. So to illustrate this pH example, we are going to learn how to neutralize a 1 molar solution of acetic acid. So we're going to go back to software. We're going to add a new stream. So right click on add a stream, not right click, double click on the add a stream button. And then rename this set pH. Okay. And for this calculation, we are also going to use the MSC framework. So click on MSC. And again, we're going to leave this default 55, 25 C, 1 atmosphere. But down here, we are going to add our chemistry. That chemistry is acetic acid. You can type it like that, just like the name, acetic acid. Is also valid if you enter components in this way. And you'll see that once I hit enter, the software will change it to the formula default, okay? Because that's how we have defined how we want to show the formula names in the software, which is not formula names, but the species name in the software as a formula. So we are going to enter 1 mole of this acetic acid, okay? And then we're good. We're not going to change units. We're not going to change anything else. So we're going to go to Add Calculation and select the option Single Point, okay? And let's run first this isothermal calculation. Let's rename this isothermal calculation. Isothermal. Why am I saying, oops, I cannot repeat the name. Okay, so isothermal -1. It's like that. I cannot repeat a name, apparently. So let's trick the system. Just put an underscore 1, and that will work. Okay, so what what we're going to do in here is, okay, let's do an isothermal just because I want to understand the original pH of this solution. Because if I want to neutralize it, I need to understand the original system. So the pH of this solution is 2.4. Okay, that's very acidic. Definitely needs neutralization. And let's go to the report and see what's going on in the species output. Okay, or yeah, let's stay in the report. Okay, so in here you'll see this is the acetic acid. Now maybe let's go back to definition and let's go to the output tab instead, because it's easier for us to follow the names. So let's go to output, right click on sections, and then click the option liquid 1. So let's now go to the report. Let's go back to our output. So make sure that you select output. You're not in the input. You select output tab, right click on the gray area, select sections, and then go to liquid 1. Okay. That will bring a new table here. And what I like about this is because if you hover over this, it will tell you the species, right? The name of the species. So you don't have to guess. So for this example, you see that acetic acid here, the second component, is 0.99. And remember, we enter 1 mole. So that means that most of the acetic acid is remaining in solution. It has not, we know that it's a weak acid, but you can see here that most of it stays in solution. Only a little bit deprotonates here. So that is the acetate ion here. And it's a small amount, 4.5, 10 to the minus 3 moles. And then we have the hydronium ion, and we have the another acetate form here, and we have also the acetic acid dimer. All of this is a very small amount, okay? So really what is contributing to my high pH here is this acetic acid. No, sorry, not high pH. My low pH here is this acetic acid. So we need to neutralize this acetic acid, okay? This 0.99 moles. So we go back to our input tab in here. Then what we're going to do is let's click on the set pH stream, and let's add another single point calculation. And this time we're going to change this type of calculation to set pH, okay? And we're going to send it to change it to set pH. So for that, we are going to change this name here, just to follow what we're doing. We're going to say that this is acetic acid neutralized. A long name, but I like it because it reminds me of what we are doing there. Okay, so once we selected the set pH, notice what has happened on my screen, on the workspace, okay? So now we have a new section here. It's called calculation parameters. So you'll see the first option, and let me increase this. I don't know why it doesn't stay big. I wish it stayed big so it's easier to present to you. Okay, so the first row here is the target pH, okay? So we need to neutralize this. We want to neutralize this, so the target pH will be 7, right? So you just enter 7. Okay, then the software says use a single titrant. There are 2 options. There is the no and there is the yes. I prefer the no option, meaning that the software, it knows. Okay, let me just show you the yes, so that I can explain it easier. So when you say use single titrant and you say yes, I want to use only 1 titrant, the software will select one single titrant. In this case, it will be HCl, but let's say you want to change it to sulfuric acid. So you can simply type here in inflows H2SO4, and you can change it to H2SO4, okay? But again, maybe if you want to neutralize, you don't want an acid. you want a base, okay? Because you have an acidic solution, so you want to add a base. You could change it for a base, sodium hydroxide. Let's say we add it here in the inflows. Go to the base, sodium hydroxide, and now you can do neutralization. However, if you leave it in no, in the option no, the software will have both the acid and the base, and it will know, it is smart enough to know which one does it need for the calculation, okay? So I personally prefer to use single titrant, the option no. I don't change it, I just leave it like that. And the software will pick the titrant that it needs to do the neutralization. So in this case, I just want sodium hydroxide as my base. The target pH is 7. And these two components here, I don't need them anymore, so I'm going to delete them. And I'm going to go ahead and calculate. Good. So again, we go to the Output tab. And we can go to Sections, right-click on the gray area, Sections, and select the liquid 1 or aqueous phase. And in here, now you see what happened, okay? So it means in here that, okay, let's see. So now this is the acetate ion. Acetate ion is a very high amount. The acetic acid has been deprotonated. It's no longer acetic acid anymore at this pH, and it's a big amount, 0.86 moles. We are forming sodium acetate, also a high amount, I would say 0.12 moles. So if you add these two, that's around 0.98 moles. So this is basically saying that all the acetate, the acetic acid, was converted into the deprotonated form and in the sodium acetate. So it no longer contributes to a low pH. Look at the acetic acid here. Now it's a very small amount, 0.013. Okay? So by adding sodium hydroxide into the solution, now again we have deprotonated this acetic acid and we have formed the sodium acetate. So that will increase, or it will decrease the amount of hydromium ion, and my pH now is going to be 7. Notice that the amount of titrant added here is 0.98 moles. So that means that in order to neutralize a solution of acetic acid that is 1 molar, you need almost 0.99 moles of sodium hydroxide to neutralize the solution. Okay? So let's go back to the input. The reason why I wanted to show you how to set up this set pH is because when we are doing corrosion rate calculations, we will want to change the target pH of a specific calculation. So you will need to understand how to set up this calculation. Okay, I have a question from an attendee here. It says, on my liquid 1, all numbers are 0. You mean in your output tab, this liquid 1 mole? I wonder why. Okay, maybe let's check that your acetic acid here, that you are defining 1 mole, and that you are also defining the amount of water, 1 kilogram of water for this stream. Maybe at the stream level, make sure that you have those two values set up. If there is a liquid 1, 0, that would be the explanation why you're seeing those values at 0. If not, let me know. You can send me a screenshot to see exactly how you have it defined, and I can help you from there. Okay, so that was a set pH And now what we are going to do is to learn how to set up an actual corrosion rate calculation. Next class, I will cover the survey calculations, which are also very, very important for our corrosion calculations. But let's start with some basics of how to set up the corrosion rate calculation. Okay, there is a question here that says that how did you increase the font size of the table? I like to increase the font size because it's easier to see. So what I do is I hold onto my control key in my keyboard, and then I just increase or decrease with the wheel of my mouse. So to increase, I go up, and to decrease, I go down. Okay, but all the time I am holding my control key. Okay, and then I just move the wheel of the mouse to increase and decrease. The only downside is that when you change, it will go back to, when you change the window, it will go back to its original size. So it's something that I want to submit to the developers so that you can keep this size. Okay, the other question is that they are still seeing zeros in the inflows, no, in the output for liquid 1. What else can it be? Let me think. 56. Yeah, maybe let's check some amounts. Let me see. Still zeros. If you could send, how can I ask for this? We have two options. You can either send me screenshot to this address, or you can just go ahead and share your screen, and then we can troubleshoot what is happening, what you're seeing in your screen. Yeah, you need to make sure that you are in your output tab here. So make sure that you are not in input, because in input, if your liquid 1 is all zeros, oh, I see what's happening. So yes, always make sure that you go to the output tab to get the results, because in the input tab, nothing has happened. The calculation really doesn't happen. The calculation happens in the output tab. So yeah, you're right. Go to the output tab. Thank you, Mike, for highlighting that. So once again, make sure that you go to the output tab down here. Don't stay in the input, go to the output tab, and then you can see the liquid 1 values, okay? Great, that's good. Okay, so with this, learning how to set up simple single point calculations can help us now to understand how to set up corrosion rate calculations. One thing I want to highlight once again is that now that we transition to the corrosion rate calculations, we will be working with the AQ framework only. No MSC, no MSC SRK. MSC will be available later in maybe next year, maybe the 24 months, no, 12 months from now, or maybe 24, I don't know, it's hard to tell. But the good thing about the MSC framework, if we have it available, is that we will be able to calculate corrosion rates in other solutions that are not only aqueous, right? So let's say you have sulfuric acid, or you have hydrogen fluoride, okay? Those that are pure components like that, pure solvents, now that will enable us to calculate those type of corrosion rates. At the moment, we are only going to calculate corrosion rates that are surrounded by an aqueous phase. Okay, so I'm looking forward to that MSc corrosion at some point. So, okay, let's start with our first easy corrosion rate calculation. I will explain how to navigate the workspace and what every single one of our definitions mean, or sections mean. Okay, so for this calculation, what we are going to do is we are going to create a new stream or add a new stream. And we're going to rename it corrosion rate. Okay, for this corrosion rate, we are going to make sure that you select the AQ framework, or you will always receive an error message saying that you cannot calculate the corrosion rate. We are going to change the units as well. So let's go to the units manager here in my CF icon, click on it. And let's change this to metric batch mass fraction. Mass fraction happens to be the first one in the list up here. To select mass fraction. And then one more change I want to do here. Usually, and I don't know if this is true around the world, but when we are referring to corrosion rates, we refer to them as mils per year, or MPYs. So I personally prefer to see the units in those specific units for the corrosion rate. So what we are going to do is to go to the Customize button. And you'll see that so far we have been working on this composition section, but there are two more sections. There is the parameter section, where you'll change your temperature, your pressure. If you have a flowing system, is per hour, per minute, per second, and all of the other things, all of the other properties, alkalinities, densities, entropies, etc. Okay. There is a third section that is the corrosion section. So in here is where we'll change anything related to our corrosion calculations. Okay. So we have the corrosion rate, the corrosion current density, potential, etc. So in this example, I don't want to keep the corrosion rates in millimeters per year. I want to select it, I want to use the mils per year, MIL per year, this one here. So I'm going to make sure that I select it, again, is the one at the bottom, mil per year. Just make sure that you select that option. It's the only change I'm going to make here. Everything else I'm happy with, but not with the corrosion rate. So select mil per year, and then click OK. And click OK again, so that the changes are saved. So you'll see here, again, the inflows has changed to mass. My stream amount now is kilograms rather than moles, but my temperature and pressure stay the same. Okay, now for inflows, I'm going to add the following chemistry. Okay, I'm going to say I have water in my system, okay, but this will be calculated, so I don't need to worry about the amount of water there. I need to add my sodium chloride solution. So usually when we are working in the lab, we work with a 3.5 weight percent sodium chloride solution, usually. So that's what I'm going to simulate here. I'm going to say that I have sodium chloride, okay, and hit enter. And I'm going to say that the weight percent here for sodium chloride is 3.5. Okay. The next thing I want to add is, I know that in the lab, if we are not working under the aerated conditions, we will have a very small amount of oxygen present in the system or in the water, dissolved in the water. So I will account for that. I will assume that this sodium chloride solution is saturated with oxygen. So I'm going to add oxygen, O2. And I'm going to say that this would be 10 to the minus 4 weight percent. Usually this is the amount of oxygen that a solution will have. This is around 8 ppm of oxygen dissolved in solution. Okay? So that is how we define the chemistry for this specific corrosion rate calculation. Before I continue, I want you to highlight the different units here. Sometimes I get a lot of customers trying to understand what we mean by millimeters per year, micrometers per year, and mils per year. So I have made a note in here of the different corrosion rates units that we have in here in the software. Okay, so it's important to highlight. I wanted to highlight these units here. Okay, let me go back. And the next calculation is we are going to add a corrosion rate calculation. So you have two options. Like usual, you have the add calculation button here. You'll see that the last option is the corrosion rate. Or you can come here to the actions pane where you'll see the add corrosion rates button or icon. So click on that button or that icon. You'll see that immediately goes under the stream level, which is corrosion rates. Okay, so very similar to a single point calculation. Okay, so we have to do different changes here. First, let's rename this. We are going to calculate the corrosion rate of carbon steel 1018. So we are going to type the name carbon steel dash 1018. That's the corrosion rate we are going to calculate. Okay. I want you to notice something. The redox button is turned on always. At the stream level it's not, but at the corrosion rate level it is. And it will always turn on the transition metal. Okay? In this case, iron. It knows that we have oxygen, sodium, and chlorine in the system, but they are not turned on by default. Unless you know if you are having changes in the oxidation state. But at the moment, let's leave as iron there. The next thing I want you to notice is the middle of this screen. Again, I'm going to increase it. This is familiar already. This is from the single point calculation, the stream parameters. This is familiar too, the inflows. But there are two new different sections. That is the calculation parameter that includes the flow type, and there is the effect of iron carbonate and iron sulfide scales on corrosion rates. By default, the software in flow type selects the static option, okay, as the flow type. But if you click on the static option, you'll see that there is a drop-down arrow, okay, and if you click on it, you'll see the different options. There are, I think, 7 different options to define the flow type or to define the fluid dynamics of the system. So you know that fluid dynamics have a significant impact on the corrosion rate because it improves the mass transfer of reactive species to the metal surface. Okay, so the first one is the static, which is representing a stagnant fluid. The solution is not flowing in this calculation, and only diffusion is affecting the mass transfer. Then you have the pipe flow. Pipe flow is basically fluid flowing through a pipe. And if you happen to select the pipe flow, then you'll see that you would need to define the pipe diameter and the pipe flow velocity. They must be defined. If you are doing a rotating disc electrode experiment, this will reproduce this type of experiment of rotating disc that we use in the laboratory. And usually a disc is rotated to bring fluid to the surface of the electrode in a predictable manner. So you will need to define the disc diameter and the disc rotation speed. If you are using a rotating cylinder electrode, it will be the same thing, rotor diameter, rotor rotation, and so on. You have the complete agitation, for example. In this case, the calculation is going to assume that the liquid phase is completely agitated and no mass transfer limitations apply, okay? And I really haven't played with these options down here, the defined shear stress. I suppose that you just define a shear stress here for the option, the defined shear stress. And this approximate multi-phase flow, this one is if you have both liquid and gas flowing in the same pipe. So those are the options. For this specific example, we're going to stay with the simple one, the static option, okay? So go back and select the static, make sure that you have a static. And then there is a second part here, which is the effect of iron carbonate and iron sulfide on corrosion rates, okay? So what this really means, and the option is include, the default option is include. And what this really means is that if you happen to have in your chemistry, in your inflows, you happen to have CO2 and H2S, the software will include the formation of iron carbonate and iron sulfide scales in the chemistry. Or, yeah, the formation of these iron carbonate and iron sulfide scales on the electrode surface. Okay, and we know that when we have some concentration of CO2 and H2S, there is a concentration limit at which these scales will be protective to the metal. So if you don't want to include the effect of these scales, then you'll have the option to exclude the effect of those scales. But generally, we have it as an include because if you have some concentration of H2S and CO2, we know that those scales will form on the electrode surface, okay? For this example, we don't have H2S or CO2, so if we select exclude or include, the results will be the same, okay? Finally, you have the contact surface down here. The contact surface is another way of saying, here is where we define the material under study, okay? It could be an alloy, it could be an element. By default, the software selects the carbon steel, carbon steel 10100. We call it the generic carbon steel, okay? And this is the default one, but if you want to change it, you just click on it. And then you're going to use the drop-down arrow. And down here, you'll see all of the different alloys that we have in here. So there are 28 different alloys. We have carbon steel, stainless steel, duplex. These ones were recently added, the Super 13 chrome, Super 15 chrome, Super 17 chrome. Some aluminum alloys, nickel alloys, hastelloys, and copper nickel alloys. Okay, so we have those. We have those, and all of them have been validated with experimental data. For this specific example, we're going to change the contact surface. We're going to change it to carbon steel 1018. So make sure that you look for it. I think it's 1, 2, 3, 4. Is the fixed option? Oops, I lost it. Carbon steel 1018 is the one that is below the 10100, the generic one. And make sure that you have selected the carbon steel 1018. To the right, you'll see that it's very similar to a single point. The default always is to calculate the corrosion rates as a function of temperature. But in this case, I want to calculate a single point rate. So just click on temperature and make sure that you select single point rate. Okay. And now we're ready to calculate. You'll see that there is the calculate button here. We can go ahead and calculate. Okay. So once the calculation is done, then we have different ways to analyze the results in this table, in this software. We not only have the report, which is the one that we have been familiar with, or have learned today how to interpret, but we also have the general corrosion rate tab, the localized corrosion tab, and the polarization curve. Okay, so we have that. Let's start with the general corrosion rate tab. Okay, so in the general corrosion rate tab, the default plot is usually corrosion rate as a function of temperature, but we are only calculating one single point. So in here, what we need to do is to make sure that we see the table form, the tabulated form, rather than the plot version of the results. So what we're going to do is we're going to click on this view data. Okay, so once we go to the view data, then you'll see that these are the results for the corrosion rate. At a temperature of 25 degrees C, the corrosion rate is 5 mils per year, and the pH is around 7. Okay, so that is the predicted corrosion rate. Then we have the localized corrosion rate. Okay, again, this is the tabulated form. This is the plot form. We want the tabulated form. And let's click on the View Data button. And in here, you will see 3 different values that are reported besides temperature. So we have the corrosion potential, we have the repassivation potential, and we have the maximum peak current density. Okay. Now, what these things mean? What do we mean by corrosion potential, repassivation potential, and maximum peak current density? Okay, so corrosion potential is, again, you have your electrode surface in your bulk solution, which in this case is sodium chloride and oxygen. And we have left the sample there, and it has reached, not an equilibrium, but it has reached a rest potential with this bulk solution. And this is the potential that is measured on the electrode surface. So corrosion potential could be the same as open circuit potential, OCP. Repassivation potential. This is a term that it also refers to protection potential. And the protection potential is when, let me think about this. So the repassivation potential is the potential that will help you to understand if you will have localized corrosion damage or not. If you exceed your repassivation potential, if you go above that repassivation potential, localized corrosion damage such as pitting, for example, will occur. If you have if you are below this repassivation potential, so you don't have susceptibility to localized corrosion damage. And so that's why we also call it protection potential, because if we are below that potential, then we are protecting our material against localized corrosion damage. Okay? And I will explain this repassivation potential in more detail in the next class. I will go through more details about this. So in this case, the repassivation potential is lower than the corrosion potential. So that means that this will drive to localized corrosion, because my material has a potential that is more positive than my repassivation potential. As I said, if you are above the repassivation potential, then you will have localized corrosion damage. Let me show you that specific formula here, or criterion in here. So if your corrosion potential happens to be more positive than your repassivation potential, then you will have propensity to localized corrosion damage. Okay? So that's what we're seeing here. the corrosion potential is more positive than the repassivation potential. Hence, corrosion happens much more faster than repassivation. Hence, you have localized damage. And the third column is the peak current density that is being generated from the worst case scenario, from the worst case peak that you could have on that electrode surface. So in here it's saying that the maximum peak current density is 0.05 amperes per square meter. Because we are predicting localized corrosion damage, the peak current density that is predicted is this value. Okay? And again, I will spend more time next time explaining how to interpret these results. Finally, you have here the polarization curve plot. And I really like this plot because in here you have the contributions of the different half reactions that are contributing to this corroding system. Okay, so in here you'll see the anionic dissolution of iron. You will see the reduction of hydrogen, the reduction of oxygen, etc. And all of these half reactions are being calculated, and all of them are put together, and then we are having our polarization curve in here, the red one, which is the one that we see in a potential dynamic experiment. So let me show you in more detail what I mean here. So let's say I want to understand, and we will go through this next class as well, just to understand it in more detail. So let's say we want to understand what is the oxidation behavior of the carbon steel. So that is my oxidation half reaction of iron. Then we have the reduction of hydrogen. So we see it here. Then we have the reduction of water. We also have, I think the oxidation of oxygen, the reduction of oxygen, and down up here we have the oxidation of water. Okay, and all of these then are put all together. At each potential, we add up every single current, a specific potential, and that's the net current density. Okay, so that will be this red curve here that is putting all the currents all together to give us this final polarization curve. That is the one, as I just said, that is the one that we usually see in our potential dynamic experiments. Then we have the corrosion potential, and that corrosion potential is represented by this triangle here, and I'm going to click OK. And in here, this corrosion potential, then the corresponding current, the corrosion current density here, then is used to calculate the corrosion rate that we originally showed here in the general corrosion rate. And that corrosion current density is translated into a corrosion rate using the Faraday's law. Okay? So that is about the results here. We go back to the definition, and I see some questions that I'm going to ask to answer. Okay, let me see. So the first question is, I am testing here the same options for this corrosion rate calculation, but my calculate button is yellow instead of green. For carbon steel, well, first let's make sure that we have the version 10. In some versions of the software that are not version 10, we haven't calibrated some of the parameters for the corrosion rate. So sometimes if you have the yellow button, that means you may have a specific warning here saying that we haven't calibrated a specific element or a specific species for the corrosion rate calculation. What else can cause the yellow button? I'm thinking. Yeah, I don't know. If you see a specific warning here, let me know, because that will indicate that we haven't defined something, or maybe something is out of range, and that's why it's giving you that yellow calculate button. A yellow calculate button still will calculate the results for you. It's just that as in some cases you have a warning. Okay, let me see. There are species for which the kinetic data has not been calibrated. Yeah. Right. So that's the warning. Yeah. That will be the warning. That some species haven't been calibrated for the um, um, corrosion rate calculations. So that's why it's saying that maybe the results will not match or will be not as accurate, right? But I wonder why, if you had the same chemistry, why you're receiving the same that warning, and I am not. So I will need to find out why it's giving you that. Because for sodium chloride, we definitely have studied that system for carbon steel 1018. Okay, so I have another question. In the repassivation curve, where can we see the repassivation potential? Okay, I think that in the polarization curve, there is another curve that is called the peak current density option. Let me see. Where I can barely see it. Let me see. Yes. So you'll see here that there is the anodic dissolution of and I need to put the corrosion potential, right? So you have the corrosion potential, and you also have this peak current density. I will need to find out if this peak current density is the potential is where and this potential, yeah, I need to find out exactly if this peak current density will give you that repassivation potential. I know that we calculated based on this peak current density theory, but I don't see how it can be interpreted from the polarization curve. I will be back with that answer next class for you. Thank you for that question. That's a very good question. What is the estimated error for these results? For these results, well, we will need to compare it with, we have used experimental data to predict this corrosion rate. The best we can do is always provide to you what we call validation plots. Okay, so these validation plots basically have or take into account all the experimental data that we have taken from the literature, and we put the model, or we overlapped our predictions from the model on those plots. So you can see how far away our predictions are. Okay, so maybe next class I can also show different validation plots that we have for different systems, so that you can have an idea of what will be the error that these results will have for the calculations of the corrosion rate. Okay, so I think, let me just write down the two questions: the repassivation potential in the polarization curve, and the error. So I will bring the validation plots. And it's something that I want to highlight here with the validation plots. We will always provide to you these validation plots. I think it depends on the service level, but let's say if you want to see a specific system, I don't know, this specific carbon steel and sodium chloride, we can always provide those validation plots to you. Okay? Okay, so I think that this is good enough for today. next class, we will go much more into detail about how to interpret corrosion rates and polarization curves, and also the localized corrosion potential, the prediction of localized corrosion, and then we will also learn how to interpret the pore bay diagrams. And that's it for me. I will give it back to Mike if you have any comments. Thank you so much for your time, and I'll see you next class. So I'll give it back to you.
Yeah, thanks, Diana. So everyone, the only thing I would say to wrap up is you've got the rest of today and tomorrow that are free. And so if you do have the time, we recommend trying to work with the software a bit. You can practice some of the things that Diana showed today. You can go through some of your own cases if you like. And then what we would like to do is bring those questions to us on Wednesday at the same time. We'll start at the same time. And then if you can bring your questions, then we'll start that class with your questions so that we can kind of begin with those, make sure everyone is clear, and then we'll go into the material. So try and work on that in the next day and a half or so. And then thanks again, everybody, for joining us today. We'll see you Wednesday at the same time. Thanks, and talk to you then.
Thank you so much.